All right, we'll start. Okay, before we start, is there any questions about anything from last week or? Nope. The final exam date is out. I can't remember if I mentioned it last class, but I'll just show it to you again. So it's here, April 23rd. It starts at 9, so just keep that in mind. So it's a little earlier. Yeah. Yeah. So I do, yeah, so I don't know why, so I don't know why they don't post the room here, but they send an email to you with the room. They sent me an email with the room, and I'll put the room on Moodle. I just haven't done it yet. Yeah. And whatever you said, EV, whatever, sounds right. I think all the INSE ones are in one of two rooms, which is the ground floor of the EV building, but it's on the art side, fine art side. So it's like, there's sort of like a hallway with like the gallery. Yeah. It's kind of across from there. That's where,
and also, is the final going to be kind of similar to the midterm format-wise and like, I guess, question-wise?
So similar, yes. So I'll add some short answer questions. Yeah. So that will be.
It's going to be like one word or one concept, or it's not going to be like super long answer?
It's not going to be long answer like write out 4 pages of equations or something like that. It might be like 2 or 3 marks, like where there's 3 concepts that you would get the mark for. But like a short answer would be like a half page kind of type of thing. Yeah. And then there'll still be a lot of multiple choice true false, and that will be similar to the midterm, like in the same style as the midterm. Yeah. Okay. Other questions? Yeah, so it starts at 9 a.m. It should be a Thursday because today's a Thursday. Yeah, it is. Okay, yeah. April 23rd. And the room number I'll put on Moodle. Okay, so we'll pick up from last week. I took some time to pre-populate the notes. So if you're trying to write it all down, you might want to just get the PDF off the email. It just means I'll be able to go through it a little bit faster. I didn't do the whole lecture, but I did the first half. Okay, so I started with what we discussed last class. So here's the circuit, same inputs, same outputs. I changed the modulus. So first off, I made a mistake last week. I said mod 96, it should have been 97. The modulus always has to be a prime number. So in the previous lecture it's 97, but this time I changed it to 61. The reason is because we have an array of size 15, and I want to have a root of unity that works with that. It doesn't matter what those things mean. Point is I just changed it, so whatever. Okay, so now we're working in Z61. So that means all operations that we do are mod 61. And it also means when we talk about Q is 61 as well. Okay. Later, when we turn the circuit, we're going to turn the circuit into a set of arrays. We're going to turn the set of arrays into polynomials, and then the polynomials into commitments to the polynomials. So that's a way of getting a commitment to the circuit. At the step where we turn it into polynomials, we're going to need this omega value. So I'm going to choose 22, and the order of 22 is 15. Okay, and the reason I want the order to be 15 is because I have 15. I have 5 gates. They all have like 2 inputs, 1 output, so there are 3 things. So this array is size 15. So now my omega will wrap. So when I go from here, the next element will go back to the start. So I'll show you that when we use it. But anyways, so 22 is a number that you can use that has order 15 mod 61. So actually here I'll just add in ZQ. Okay. And so you can just sort of see it with your eyes. 61 is a prime number. If I subtract 1 from it, I get 60. And so every divisor of 60, there'll be a group of that order. So 15 clearly divides 60, right? So 30 would divide 60, 15 would divide it, 3 would divide it. So you're going to have a bunch of different sizes of orders, subgroup sizes. So 15 is going to be one of them. Okay.
Was there any science to choosing the 22 number?
Yeah. So you, there's a couple ways. So I didn't go through like the way that you would get a computer to do it because it's too complicated. So what I would suggest is just doing exhaustive search. So just start at w equals 1, w equals 2, w equals 3. At every value, what you do is you raise it to the power of what you're looking for. So if I'm looking for a root of unity of size 15, I'm going to raise it to the 15. I'm looking for it to come out to be 1, which is the same as omega to the 0. Yeah. But if I find it equals 1, that means that it's either 15, but it could also be a divisor of 15 as well. So it might be an order 3 that's repeating 5 times, or order 5 that's repeating 3 times. So I also have to check those as well and make sure it's not repeating early. Yeah. So that's basically, for the purposes of this course, this is how you do it. There's techniques that are slightly faster than that, but they're a little more complicated. Okay. And everything about Q and omega is public information. The verifier knows it. That's like the part of the crypto setup, so they all agree on what that looks like. Okay, the next step, we're going to take this circuit and we're going to put it into the form of one or a couple arrays. All right, so we talked about last class. What we will do is the verifier will know some of these inputs. So they know the 3, the 5, the 6, and the 7, so I've done those in green. They know that 32 should come out the other end. So by the way, 32 I changed. Last class it was 22 because the modulus was different. This week it's 32 just because it's mod 61. None of the other values are greater than 61, so they don't change. So I fill it in, so I do the left input, right input, output of gate 1, the left input, the right input, the output of gate 2, and I keep going. And I wrote the word verifier key. That's sort of a technical term, but it means everything the verifier knows. Okay, so the verifier knows what gate is what gate. If one of the inputs is public, then they know those inputs. If one of the outputs is public, they know that output. What they don't know is what we call the trace, or all the internal values. Okay, they don't know it either because they're secret, and they may not know some of the inputs as well. So some of these inputs may be secret. So if you reveal the internal values and some of the inputs are secret, you can figure out what the secret input is based on the internal values. So that's why we don't, in the secret case, we don't reveal the internal values. And even in a case where the verifier knows all the inputs, they know all the outputs, they know the function, they know everything, they could compute it themselves, right? We might still use this technique if we want to save them time. Okay, so in that case, you can think of the pink values as not secrets, they're just too much stuff that the verifier doesn't want to look at. Okay, the verifier wants to know that all these values are filled in correctly without actually looking at any of them. Yeah. Would they know which, sorry? Yeah, so the statement that I'm proving is for this function, for this circuit, think of this circuit as a function. This function with inputs 3, 5, 6, 7 equals 32. So that's the statement that I'm proving to the 32 is green. Yeah, so sorry, green means you know it, and pink means you don't know it. Did I do it right?
I mean, like on the, what you actually visualize.
Oh, here, yes, yeah, sure, yeah. Yeah, so I'll make it black. Yeah. Okay, so everyone's good with how we make the circuit? Okay. Then what we want to do is we want to mark which gates are additions and which ones are multiplications. So that's something that's not encoded yet. So the way we're going to do it, Plonk does it a little more efficiently, but this is a sufficient way of doing it, is we're just going to have an array for all the gates that are additions, and we're going to encode 1, 0, 0. And if it's a multiplication gate, we'll encode all zeros. And then we'll do the same for all the multiplication gates. And so these two vectors or arrays are sort of complementary to each other. Technically, if you had one, you wouldn't necessarily need the other, but it's convenient to have both of them. Verifier knows these polynomials, or these vectors, yeah.
Have you uploaded both the PDFs, like the previous one and then this one as well?
Sorry, so I just didn't get the question.
Have you uploaded both the PDFs? Like I think this is different from the last one. So have you uploaded both of them?
So I have not uploaded this. This is like today's lecture notes, but I will upload it. Yeah. So I'll add some stuff to the end and I'll kind of write over top of it. Okay. Okay. And then the final thing we need is this. This information tells you a lot about the circuit, but the one thing it's missing is it doesn't tell you that the output of gate 1 is the left input of gate 4. Okay? So if I opened this array up and looked at all the values, I could see that there's an 8 here and it gets copied here. But if I'm not looking at the pink values, then I don't know whether that's true or not. Okay?
Sorry.
Yeah.
The green stuff is what the verifier knows, right?
Green is what the verifier knows. Yeah.
How come he knows this 5 out there that seems to be like very deep inside the circuit?
Yeah, so that's a consequence of me pulling the 5 all the way down here.
Right.
Yeah.
We haven't covered yet how we describe the wirings, right?
Correct. Yes. Yeah. And I'll make this black just to be consistent. Yeah. So it's kind of weird that the 5 is this deep, but that's why. It's because I carried it over here. Okay. So for the wiring, this isn't how we're doing it. This is just sort of a visualization. Also, I didn't really mark which ones are inputs or which ones are outputs. So what I did is I kind of took a copy of C, and I'm just reminding you, the verifier knows that the first input goes here. They know this is an input, this is an input, this is an input, this is an input, and this is an output. They actually know that already because they know which gate is which. But anyways, I'll just make it explicit. And then I drew in what the wiring looks like. So this value here also needs to show up here. And the output of this first gate is fed into the input of the third gate. So I just sort of drew an arrow between it. But I don't know how to commit to a set of arrows. They're not numbers, right? So what I want to do is I want to have an array of numbers. I want to commit to that. And if I can commit to that, then I can represent the wiring. So this is like, we'll call it work in progress. So this, I'm just showing you that we're going to need some representation of it. But effectively, you should be able to look at whatever representation I give you and draw this diagram as a consequence, but it might not exactly look like that. Okay, wiring is hard, so we're saving it, although we'll start talking about it today. But that's why we're sort of punting on the wiring for now. Let's just try and make sure that we can do stuff with these first 3 vectors. Okay. This I'm just going to remove because I kind of did the diagram different. Okay. So green stuff verifier knows. We call it a verifier key. It's not like a cryptographic key per se. It's just like a set of values that they know before they start. And then witness is the term that we use for values that we're not showing to the verifier, either because they're secret or because the verifier doesn't have time to look at them all. Okay, questions about this representation? Okay, so what we're going to do is the prover is going to turn, what the prover wants to do is they want to give these values to the verifier. Okay, so there's a couple ways they could do it. They could just give the raw values, but then it's going to be the same size as the witness. So the longer the array, you're giving the verifier something of that size. Okay, so what I want to do is I want to give the verifier a succinct commitment to these values, as opposed to giving them the raw values themselves. I don't have a way, you haven't seen it in this class anyway, of committing to an array, other than maybe like just hashing the whole thing or something like that. But I want to do a little more than just give a commitment to the array. I want to be able to reason about what's happening inside the array and have some math that works on top of the commitment. So my idea is I'm going to turn this into a polynomial. Then I'm going to commit to the polynomial because I have the ability to commit to polynomials. Once I have a commitment to a polynomial, I can do things like multiply commitments together and add commitments together and things like that. And that's going to allow me to prove possibly that this is constructed correctly for that. Okay? So step one is I want to turn this into a polynomial. How do I do it? So I have these values. There's 15 values, and I just want to put those 15 values into a polynomial. I'm going to commit to that polynomial. I'm going to give it to the verifier and say this represents those 15 values. Okay. Okay, so I could put it in the coefficients of the polynomial. That's a valid approach, but it's not going to work for us in the end. So we will see later one place where we do that approach. So that was one of the three ways where we could do it. So I'm not going to do that way now. Yeah? What's another way that I could put 15 values into a polynomial?
1, 0 equal to like first value and then.
Okay, so I can make these the points on the polynomial, the y values of the polynomial. But then I need a set of x values. That's called the domain. And then I'm going to draw, which is called interpolation. I'm going to draw the curve through it. And then that's going to represent my polynomial. So that is what we're going to do. Okay. The third way is I could put it into the roots of the polynomial where it crosses 0. Again, that's something we'll use a little later, but we're not going to use it now. For now, we're just going to stick to programming it. Okay. All right. So now I have the y values for my polynomial. I need the x values. Okay. So the x values are the domain. And so a simple approach would be 0, 1, 2, 3, 4, up to 14. Okay? But later it'll be nice and convenient if I have a way when I move from this value to this value to this value, and I hit the end, and I go to the next value, I kind of circle back to the start. That would be nice. Okay? So that's why we have this root of unity. So the root of unity is 22. Okay? And so the domain. So first off, I'll just say that what I'm doing is I'm going to commit to each of these three vectors. The W1 we'll worry about later. So I have the circuit trace. I have what we call a selector that selects the addition gates. And I have a binary selector for the multiplication gates. All three of them I'm going to turn into polynomials. Okay. So the domain I'm going to use is I'm going to use omega to the 0, omega to the 1, omega to the 2, omega to the 3, all the way to omega to the 14. Okay? Now, if omega equals 22, you can work that out. What is omega? What's 22 to the power of 0 mod 61? And the answer is 1. What's 22 to the power of 1 mod 61? It's 22. What's 22 squared mod 61? It turns out to be 57. So you can check these numbers, but they should be right. Okay. Let's say that I'm at this x value. So I'm at or let's go to where the 8 is. So I'm at the third cell in my array, and I want to go to the fourth cell. Okay. So the third cell I've encoded at the value 57. Now I want to figure out where did I encode the next cell? How do I go from 57 to 34? Say it louder. So it's not +1 though. If it was +1, then it would be 57 to 58. So notice it's not +1, but that's the right idea.
Mod Q here, then it's so W to the 3 and then to the Q and then we get 24.
Okay, so everything is mod Q, but how do I get from 57 to 34? So it's not 57 plus 1 mod Q. That would still be 58.
No, it's omega.
W.
Times omega again.
Okay, so what I'm doing is I'm multiplying by omega, right? So I start at 1, I multiply by omega, I go to 22. What's 22 times 22 mod 61? Well, it's 57. 57 times 22 is 34. 34 times 22 is 16. Does that make sense? Okay, so let me just kind of grab this and just say that 16 times omega equals 47. Okay, so that's how I'm moving. So it's very easy. You tell me 22, where do I start? You tell me the value 22, and or actually, let me put it a different way. You tell me the number 22, and we start at 1, then I can compute this sequence just by multiplying by 22, and I'll get the sequence. And then what happens at the end? So 25 times omega equals 25 times 22. What does that give me? So by definition, it's going to give me 1. Okay? Why is it going to give me 1? Well, this is the same as omega to the 14. Omega to the 14 times omega is omega to the 15, right? And what did we say here? We said that if the order of omega is 15, then omega to the 15 is the same as omega to the 0. Okay. So we defined it that way. And so 25 times 22 will equal 1. So we'll circle back and we'll go back to the first value.
This is given that the order is 15.
Yeah, so this, exactly. So if omega did not have order 15, that trick does not work. So that's why we spent a lot of time. We didn't spend that much time, but we were talking about roots of unity and modular subgroups and all that. All of that, like math, really just came down to being able to do this trick of when I increment my counter by multiplying by omega, I wrap back to the start. Okay, you don't strictly need that, but it helps with performance and it helps you as a student sort of visualize what's going on. There are ways of working around it if you don't have it, but anyways, yeah.
So that you would choose omega depending on the size of the array.
Exactly. Yeah.
You have the exact order.
Yeah. So you would figure out the order of the array that you wanted, and then you would choose an omega that fits. Yeah. Now in real life, that's harder than it sounds because the omegas that you have available are usually not divisible by 3. They're usually divisible by 2. And even if they're divisible by 2, your array isn't going to be the exact size that you want. So what you're going to do is you're going to do something where you kind of add padding bits on the end. But then when you want to prove things, you have to take care of those padding bits. Yeah, and so it gets a little more complicated. But for this class, like just to get through Plonk from start to finish, we're just going to assume that, that we know the array is size 15, and we have an omega that has order 15 as well. Yeah.
I made it in like exact property, but the 22, is it like the value you have to define, like with I think you mentioned earlier, like exhaustive search, or is it just like a value you can easily calculate?
So omega is something that you would have to find. Okay. So I would have to find that I would have to find something of order 15 in Z61. Yeah, and so I would have to brute force that, essentially. Yeah.
Did you say that order 3 or 5 would also be good?
Yeah, so there'll be, it's all the divisors of Q minus 1. So every divisor of 60, there's going to be
4 also.
60 is divisible by 4?
15. 4, 15.
Yeah, sorry, yeah, of course, yeah, exactly, yeah. So so this will have divisors 1, 2, 3, 4, 5, yeah, and then 9, I don't know, anyways. It has a lot of divisors. This is actually a nice modulus to use. Yeah. Okay, so we're good. Are we good with this domain and what it's doing? Okay, so how do we use this to make a polynomial? Well, you can think of the domain as the x values, and then the values in the array are y values. Okay, so that gives us a set of points. So 1, 3 is a point, 22, 5 is a point, 57, 8 is a point. So I wrote these out here. So 1, 3, 22, 5, 57, 8, 34, 6, 16, 7, et cetera, et cetera. Okay? And then what I do is I just start graphing them. Okay? And I run my interpolation algorithm, and it's going to run a line through them. And it's going to give me the polynomial in coefficient form. So it's going to tell me what the coefficients are.
Is this a pattern, like some kind of sinusoid with the converging amplitude?
No, not at all. So it just kind of looked that way. Yeah. And it kind of goes up and down a lot. And another thing I'll note is if you actually graph this, because we're working mod 61, first off, we don't, technically there's nothing that's defined between these points, right? Because they're integers. Or sorry, it's not a continuous line. So there may be, notice that there are x values that we don't have, okay? So there's 1 is on our domain, but 2 is not on our domain, okay? The polynomial will be defined at 2. So it's going to have some value at 2. We just don't know what that value is. We don't care about what that value is. Same with 3, 4, but it's not going to be defined at 2.5 or 2.31. It's only going to be defined at integers. So when I draw the line through, it's for your education, but I can't technically draw a line through it because when you draw a line, you're saying that it's a continuous function and it's defined at all the decimal points in between. It's not defined, yeah? So it will give you something that's conceptually the same as drawing a line through, but it would look jagged, like it would just be like little segments that don't like kind of fit together if you tried to graph it. But anyways, in your mind, just think of a polynomial like this. Okay. And this is called interpolation. And because we chose a domain, because our domain is a root of unity, it wraps. It also lets us do a faster interpolation method called fast Fourier transform. So that's another benefit to setting up this omega this way, but you don't have to really worry about that. So I'll just write FFT here. Okay, so are we okay now? We understand what we're doing, right? You tell me, yes? Okay. All right, so now I have the polynomial in coefficient form. Why did I need it in coefficient form? Because I want to commit to it. So if I want to commit, I need the coefficients because that's how KZG wants me to commit to it. Okay, so that's why I did this step. And then I can do the same for S plus and SX. So notice the domain is the same. So the X values are the same, right? We always use the same domain. The difference is the Y value. So here I'm encoding 1, 0, 0, 0, 0, 0, which is the values here, 1, 0, 0, 0, 0, 0. And then for this one, I'm going to encode 0, 0, 0, 1, 0, 0, 0. And so these would be the set of points that I get here. I'll do the same step. I'll turn it into a set of polynomials. And so now I have 3 polynomials in coefficient form for the 3 arrays. Good so far? Yeah. How do we convert? So the interpolation is the algorithm where you take in a set of points and it spits out a set of coefficients. Oh yeah, so how to do interpolation? So we talked about it like a long time ago, but you basically have a big matrix, and the matrix, you multiply them together, and it does that. Yeah. Yeah, so you can go back and remind yourself, but at this point you don't really need to know how it works, just that what it's doing. Yeah.
Do we have to do such type of interpolation before we do that? Or?
No, of course not.
Okay, so just know that it's something that can be done.
Yes. Yeah. Okay. So now we have our 3 polynomials. Now I'm going to commit to these 3 polynomials. Okay. And this is what I'm going to give to the verifier. Okay. So the verifier will get this. Okay. So the verifier, in a sense, knows the circuit. They have 3 commitments. They have a commitment to this, to this, to this. They can't see every value in the commitment, and the commitment's really short, right? So, but it's it locked in the circuit. So this circuit is now locked into those 3 values. The prover can't change the circuit if it becomes inconvenient. If they want to prove, like say they want to make some of these wires wrong and then prove it to the verifier, it's too late. Okay, so they're now locked in to this exact circuit, and they can't do anything about it. Okay. So they've committed to this circuit, and the verifier holds these commitments, okay? Now what the verifier is going to do is they're going to say, all right, you need to prove to me that what you locked in is a correct circuit. Okay? And I want you to prove it to me without showing me all the pink values. Okay, I want a nice simple proof that all the pink values are right, even though I'm not going to look at them all. All right? So at a conceptual level, we need to prove 5 things to prove that the circuit's right. The first is that we're going to prove that the public inputs are correct, and the public output is correct as well. And we mentioned last time, the way we do this is we just simply open the polynomial at those points. So I'm going to open it here. I'll do it on this diagram. So the verifier knows the location where these values are, and we're just going to open them up. Okay. Now you might complain and say that doesn't sound succinct anymore. For example, the number of times I have to open it is a product. It's a function of how many inputs I have. So if I have 2 inputs, I have to do 2 openings. If I have 10,000 inputs, I have to do 10,000 openings. But what I didn't show you is that for KZG, there's something called batch openings, where you can open a whole bunch of values on the same polynomial, and you can do it more or less in the same amount of time as just opening a single point. Okay, that it's a complexity that if we had a lot of time at the end of the class, I would show it to you, but we sort of skipped over that. Okay, the other thing I would say is that for most normal circuits, the interior values, like the red values here, will be much bigger than the inputs and the outputs. Usually inputs and outputs are pretty small, and then there's a ton of intermediate stuff that's going on. And so you're trying to save the time of that.
So output is easy, right? It's just the last value of the.
Yeah, so in this circuit, I drew it where there's 1 output. You might imagine there's circuits where there's more than 1 output, then you would have to work with that. There's also ways where you can take what the output should be and subtract it from what comes out the circuit, which gives you 0, and then you just prove that the output of the circuit is 0. So there's a way to change what the circuit is so that the output is always 0, and then it becomes a little easier to prove that it's 0. But that's just don't even worry about that. But that's a more advanced concept. Okay, so are we all good with A and B? All right. So the first sort of material thing that we have to do, where we have to do a bit of work, is I want to prove that all the add gates are correct. Okay? So what that means is everything that's marked as an addition gate, 1, 0, 0, I want to prove that 8, the output is the left input plus the right input. Okay? So for this blob, I want to prove that this plus this equals this. For this blob, it's a multiplication gate, so I don't care. I'm not going to prove anything about it. I'm going to skip it. This one's an addition gate again, so I have to prove that this plus this equals this. And then this one's also addition, so I prove it, and this blob I don't care about. Okay. All right, so we worked out an equation last class. And we said that this is an equation that proves all the additions are done correctly. Okay? It says that if I take the polynomial of the circuit and I add it to it multiplied by omega on the inside, and then multiply by omega squared on the inside, I subtract that. And I multiply all of that by the selector vector. I'm going to get a bunch of zeros on the domain. On the domain means that for these values, all the values inside the array will be 0. Okay? Notice that, for example, I said the number 2 isn't on the domain. So it might not necessarily be 0 at number 2. Okay? But it will be 0 on all the domain elements itself. Okay. So what I want to do is I want to show you visually that this works. I think it's easier to visualize it. Okay? So the first thing I want to do before we visualize the whole thing is I just want to talk about this here. I mentioned it last class, but we can play with it a little more to just convince ourselves. What does this mean? Okay, I know what this means. This is a polynomial of C. It's this polynomial here, right? So this is the polynomial. I'm very comfortable with this polynomial. What I did here is I put an omega on the inside of the brackets, and now I'm not quite sure what that means anymore. Okay? So I know it's somehow related to this polynomial because it's almost the same as the polynomial, but I have this additional omega here, and that's kind of messing things up. Okay? So imagine this is just the first part of the polynomial. So at 1 we have 3, at 22 we have 5, at 57 we have 8, and at 34 we have 6. Okay, so this is the polynomial PC that we've seen already. All right, now what I want to do is I want to compute the polynomial, which is the same, but I'm going to throw an omega in here. Okay. And this whole thing is a polynomial. It's not the same polynomial as this. Because the omega is there, it's a different polynomial. So I'll call this P2. So we can call this P1. So P1 is this polynomial. P2 is P1, just with the omega here as well. Okay? Now let's just take one value and think about what happens to that one value. Okay? So let's say I want to evaluate P2 at the value 57. Okay? So P2 is the same as P1 at 57 times omega. Okay? So P2 at 57 is the same as P1 at 57 times 22. Okay? What's 57 times 22? Well, if we go up here, we know that to move here, we multiply by 22. So if I multiply 57 by 22, I'm going to get 34. Okay? So what that tells me is that P2 of 34 is 6. All right, so I wrote a 6 in here. So P2 of 57, this is P1. P2 of 57 is the same as P1 of 34. Okay, so P2 of 57 is 6, which is the same as P1 of 34. Does that make sense? So we're going to shift everything. Yep. So that's exactly what happens. So what happened is I took the 6 and I shifted it over. Okay. So P2 is P1. It's just every value is shifted over. So what's the value that would be here? So that's what this does. When I multiply by omega, okay, arithmetically, I'm multiplying by omega. Visually, what multiplying by omega does is shift. Yeah, so those two are the same. It's just, this is it in math form, and this is it in kind of visualization form. Yep. Okay, so the 8 will go here. The 5 will go here. The 3 will go all the way to the end of the array.
What's the bigger picture? Like, why we are doing this?
I'll tell you why we're doing it in a second, but I want you to have the small picture of this is what this notation means. Okay? Yeah. We did, yes. Yeah. Yeah. So everything to this point right now is reviewed. Okay? But hopefully drawn out a little better so it's less sloppy. Okay. All right, now I want to look at this equation again. Okay? So now that I know what this means, it means it's a copy of this array. It's just been shifted over by 1. What about omega squared? That's omega times omega. So I'm going to shift it over 2. Okay, so every time I add an omega in here, I shift it over 2. Okay, so what I'm going to do now is I'm going to draw out. So we have 4 arrays. Okay, and I'm going to draw them out, and then we'll consider what they look like. Okay, so this is the original array. It's the array that we had at the very top of the slide here. Okay, it's our trace of our circuit. So I have the circuit trace. Then I multiply in an omega, so it's going to shift everything over. So the 5 moved over to the first position, the 8 moved over to the second position, and the 3 went all the way to the end. Okay, that's the wrap property that we have. Okay, And when I go to omega squared here, what happens? I shift by 2. Okay? Or you can think of it as this shifted by 1. Like this is already with an omega. I'm multiplying in another omega, so I'm shifting this by 1. So you can think of this as shifted by 1 or the original shifted by 2. Okay? So this value goes to here, then it goes to here, and you can see that all the way through. Okay? So every value gets shifted over. Okay, so what I want to do is I want to take this value, I want to add it to this value and subtract this value. Okay? Then what I'm going to do is I'm going to multiply it by my selector. Okay? So here's my selector. Okay? Then whatever the result is, I'm going to write into this vector v. Good so far? Okay, so let's do it. The first thing I'll ask, I'll try and get this all on the slide. I can maybe zoom out, but can't remember how to zoom out on this. Okay, anyways, I think we can see everything that we need to see. Okay, let's say that the value at the selector is a 0. What's the value at v? 0, right? So if selector is 0, 0 times this stuff will be 0, okay? So everywhere where I have a 0 here, I can just go ahead and fill in a 0. I already know that these values are going to be 0. Okay. So the only time I'm checking this equation is when I have a 1 in the selector vector. Okay? So that happens on 3 places. There's 3 places that I have a 1. Why do I have 3 places where I have a 1? What does this selector vector represent? It's addition gates. Okay, so I have 1 in these 3 positions because these 3 positions are the start of an addition gate. Okay? So what I'm doing is, for each addition gate, what I want to do is I want to make sure that 3 plus 5 equals 8. Okay? So I want to make sure that that equation holds. Do I care that 5 plus 8 equals 6? I don't care about that because that's not an addition gate. That's like the last half of one addition gate and the first bit of the next gate, okay? And if something's a multiplication gate, like 6 times 7 is 42, I also don't want to check this rule, okay? So I want to check this rule only when I'm at the start of an addition gate. So that's what this selector vector is doing for me. It's making sure I'm only checking this equation when I'm at the start of an addition gate, okay? And the equation I'm checking is I'm checking 3 plus 5 minus 8. Okay, so what's 3 plus 5 minus 8? Is 0, right? And that's the same as checking, if I can write a 0 in here, right? That's the same as checking that 3 plus 5 equals 8. Okay, so in other words, if this vector actually turns out to be all zeros, it's if and only if these addition gates are encoded correctly. Okay, so addition gates being correct, v being 0, are the same thing.
This is done by the verifier, right?
This is done by the prover. So the prover is going to make this polynomial v, yeah? And then they're going to, again, they could commit to it and send it to the verifier. But actually, since the verifier already has commitments to this stuff, then they don't have to necessarily create this polynomial. The verifier can kind of check this relationship with what they have, which we'll see in a bit. Yeah. Okay, so does this make sense now, this visualization? So that's why this equation is true. Okay, so this equation equals 0 on the domain. And so if it's not an addition gate, the start of an addition gate, it's getting a 0 automatically. And if it is the start of an addition gate, then we're actually checking this relationship. Okay. Now, let's say an adversary comes in and they say, I'm supposed to compute 8 plus 42. It's equal to 50, right? But I'm an adversary, and so I'm going to try to prove to the verifier that this value is 51 instead of 50. Okay? How am I going to get caught? So what I'm going to have to do is I'm going to have to put the number 51 in here, right? Then if 51 is here, 51 plus 42, did I put it in the right spot? Sorry, I did it on a multiplication gate. I should do it. No, I did it. Oh, yeah, sorry. Yeah, sorry, it's right. Okay. So then this would be 51, this would be 51, this would also be 51. Okay, and let me point it into the, I'll put it into the value here just so it's clear. So this is the adversary. Okay, now let's compute what V should be just for this cell here. Okay, so 8 plus 42 is 50, minus 51 is minus 1, right? Or Q minus 1, okay? So in this case, am I going to get 0 here? I'm not. I'm going to get a Q minus 1, okay? Q is 61, so it would be 60. So I'll get the number 60 here. Okay, so if the prover lies and doesn't do an addition gate correctly, this won't end up being all zeros. Okay, now does the verifier know that this is all zeros? They don't know. Okay, so we still have to prove to the verifier that it's all zeros. Okay, what I did is I took a problem that was sort of complicated, like there's a bunch of circuits and there's a bunch of add gates. And they're all done correctly. That's kind of a messy thing to prove because there's add gates here, but then we skip them and then we have them elsewhere. So it's kind of hard to like write that out mathematically. But what I did is I turned it into a statement about here's a vector and all the values are 0. I think that will be easier to prove. So that's why I did it. So I sort of translated the statement that I wanted to into that is true if this whole thing is 0.
So this is not still a proof that verifier can check it?
So far not. So this is an intermediate step. So I took what I wanted to prove, I turned it into a statement that these are all zeros. But now what does the verifier have to do? I have to convince them that these are actually all zeros. Okay? So that's the next step. So the prover is doing it at first because remember the verifier only has commitments to these.
Yeah, and you can do computations with those.
You can do computations with the commitments. So there will be, later I'll show you what the verifier does to follow along. So basically right now the prover is just doing this. But whatever they're doing with the real polynomials, the verifier is going to kind of do in parallel with the commitments to the polynomials and make sure that it works out. Does that make sense? Yeah. Okay. So I'll show the verifier later, but right now, so far, this is just the prover. Okay. Now, before we go there, let's just talk about 3D here. So I want to prove that all the multiplication gates are correct. I'm actually going to do it the exact same way. Okay, I'm going to have an equation just like this. I'm going to make two changes to this equation. The first is I'm going to use the selector of the multiplication gates instead. Okay. And the second change, can anyone see what the second change is I have to make to this?
Multiply 1 divided.
Okay, so instead of adding here, I'm going to multiply. Okay. So I'm going to check whether this times this, it will give me something that should be here. And if I subtract the 2, then it should equal 0. Yeah. Okay, so it's almost the same. I just made these two changes to it. And now I know how to do 3C as well. This isn't a full proof yet. So again, all I've done is I've reduced it down to this being 0. But now I have to actually prove that it equals 0.
Did you say how we ended up with those equations, the 3-5 equations, these polynomial multiplications and all these operations?
So last class you mean like how did we derive these equations? So we did it last class. So I didn't say it this class how we did it, but it's more like I'm telling you what they are, and then we're checking to make sure that they are right, rather than how do you come up with them from first principles. To come up with them from first principles, you just sort of have to know. You have to know what you're doing with polynomials and why certain operations on polynomials do certain things in terms of the data. So it's like coming up with a crypto algorithm. Like there's no recipe that you follow. It's just you know a lot about the area, and then you say, if I do this, then I can see that this happens. Yeah, yeah. So like in my research personally, what we do is we pick a problem, and then we come up with these equations for that problem. So like I'm interested in voting, so I can prove that a voting system was done correctly with 15 equations that look like this. Here they are. But I had to invent those equations myself.
Okay, did you say that in the last class you talked more about how you came to invent those things or not?
Sorry, say that again.
Did you mean to say that in the previous class you explained more about how you came up with those? Or?
I think we did, but I don't remember exactly what I said last class. But I know we wrote this equation out last class.
Yeah.
I don't know how much intuition I gave to it.
I'll just read it.
Yeah. I think I might not have actually said much beyond just, this is the equation, let's see that it works. Yeah.
I plus 2 equals to I plus something like that.
Yeah. So there is a way, right, where you can start with the array math that you want to do. Like you could write this out in terms of arrays. Like I want an array, I want array plus 1, array plus 2, and then you can sort of turn the arrays into the polynomials. Yeah. Okay.
Oh, yeah, right. Yeah, it's kind of reverse, yeah.
Yes, yeah. So you kind of have like you have like what you're doing on the array side, then you're trying to match it with the polynomials, and then you're trying to match that with the commitments to the polynomials. So you're kind of doing the same algorithm 3 ways. Once with arrays, once with polynomials, once with commitments to the polynomials.
And these are called commitments.
Sorry, say again.
This is for commitments.
This line here?
Yeah.
Sorry,
So these are called commitments.
these are polynomials themselves. So when we talk about commitments, I'll change to the notation K for commitment.
Oh, okay.
But I'm going to need to check like K of S times like K of C omega. Like I'm going to have to check that with the commitments as well later. Yeah. So the verifier will check that later. Okay. So far we made some progress on it. We're not done. We're not near done yet. But any questions about this so far? Okay, so now let's think about how am I going to prove that this is 0 on, how do I prove to you, I hand you, say a commitment to this, and I'm going to prove to you that it's 0 everywhere. Okay, so just to recap, I have a statement like add gates are correct. And I turned it into a statement that's like V is 0 on the domain. Okay. By the way, the reason also why we call this V is we call this vanishing. So when you have an array that on the domain, or you have a polynomial representation of an array that's 0, we say it's a vanishing polynomial. Or it vanishes. Okay. Now, is a vanishing polynomial and a 0 polynomial the same thing? So here I have, I'll call it Z. This is what I call the 0 polynomial. Sorry,
It's like x equals to 0, right? Because all the values are zeros.
yeah, so the 0 polynomial is that. Yeah, so it's every value is 0. I'll draw it in a different color just so that you can see it. Okay, so that's the 0 polynomial. Okay, here I'm going to draw a vanishing polynomial. Is the vanishing polynomial 0 everywhere? Okay, so we know it's 0 at all of these x values. So it's going to be 0 at the x value 1. It's going to be 0 at the x value 22, 57, 34, 16. But what about the x value 2? 2 isn't on this domain. So I haven't said anything about whether it's 0 at 2. Doing this math doesn't make it 0 at 2 because this math only works on what I programmed into the domain itself. Okay? So the answer is that we cannot assume that it's 0 there. And by all probability, it's not going to be 0 there. Okay? The reason it basically cannot be 0 there is when I interpolate this polynomial, I end up with something that's degree 15 because I have 15 points. Okay, or degree 15 minus 1 or whatever. But something roughly degree 15. And a degree 15 polynomial can only cross the x-axis 15 times. Okay, so whatever the degree of the polynomial is, that's the number of times it can cross the 0, okay, or the number of roots that it can have. And so this is crossing at all the values of q. Okay, so the degree of this, well, it actually has a very low degree because it's just y equals 0. It's sort of a corner case, but anyways. Okay, so the vanishing polynomial is going to look like, let's say I have 1 is on my domain, 9, 12, 15 are on my domain. So 9, 12, 15, et cetera, et cetera. Okay, so what I'm going to do is I'm going to have a polynomial that it goes through these 0 values. But if I go and look at it, I didn't draw that very well. But if I go look at its value at, say, 10, I'll find something that's not 0 in between. Okay, so a vanishing polynomial and 0 polynomial are not the same. Okay, but what we can do is we can relate them to each other. Okay, so if I want to test whether a vanishing polynomial vanishes, actually, let me do one other thing. Okay, so this is the vanishing polynomial that came out of my math equation. Okay, and this is the 0 polynomial. There's a third thing I want to do is I want to define, I'm going to call it a known vanishing polynomial. I'll call it VH. So vanishing, H, so the domain we often call H for whatever reason, so that's just the domain. So this just means it vanishes on the domain. let's say that the verifier and the prover are both going to do this beforehand, okay? It's going to turn out to be a lot simpler than what it looks like, but I'm going to walk you through what you would have to do, and then at the end you'll see that, oh, it's actually really simple, or it ends up being something simple. Okay, so I'm going to start with my domain, which I know. My domain is 1, 22, 57, 34. Okay. And if I want to make a vanishing polynomial, what I want is I want a polynomial that's 0 at all of these values, right? Okay. So all should be 0. So VH of each of these values should give me 0, 0, 0, 0. Okay. What's a name for a point that's 0 on a polynomial? A root. If I give you a set of roots, 15 roots, and say compute the polynomial in coefficient form, how would you do it?
Like x minus the
Okay. So notice that these are all roots. And so we can define this as this minus the roots, root 1, I'll say 0. This minus root 1, this minus root 2, etc. Okay, we can start filling this in a bit. So I have this minus 1, this minus 22, this minus 52, this minus 34. Okay. And let's say I multiply this whole thing out. What do I end up with? So it turns out, this is another reason why we use omegas, these roots of unity, because there's this multiplicative relationship between them. When you multiply things, like when I multiply 22 by 52, I get another thing that's in the group. And so I sort of end up subtracting it from itself. And so because all of these are related to each other, there's going to be a ton of cancellations that happen. Okay, so what I should get is a really big, ugly equation of coefficients. But it turns out that almost all the inner products, they all cancel out with each other. Okay, so you could work this out like by hand and see it. But what we'll end up with is a very, very simple expression. We're going to end up with this to the power of k minus 1. And k here is the order of omega. So in our case, it was 15. Okay. So in other words, I'm going to have a degree k polynomial, and my polynomial is just this to the power of k minus 1. Okay, whatever the input is, and that's it. Okay. So this is a simple closed form equation for not necessarily the vanishing polynomial that I created. I created this vanishing polynomial. You can have lots of different vanishing polynomials.
valid for all of them?
Sorry.
All the vanishing polynomial is valid for all of them raised to the power k minus 1?
No, so let me say this clearly. So this is a vanishing polynomial. It's the simplest minimal vanishing polynomial. Okay? Now, we said we have this polynomial here, it vanishes, and we said, I don't care what happens at the value 2. Okay? If I set the value 2 to be 5, I get one polynomial. It's still a vanishing polynomial because I don't care about 2. But if I change the value at 2 to 10, I draw a line through it, it's still a vanishing polynomial, but it's a different polynomial because I change at least one value, the whole the polynomial changes, right? So you can have an infinite number, well, it might be finite because we're working mod q, but you can have lots and lots of polynomials that vanish, yeah? So this is one polynomial that vanishes. It's kind of the minimal polynomial that vanishes. The polynomial here also vanishes, but it might not be, it might not be exactly this. In fact, it probably won't be. It probably will have different values than this one outside of the domain. Okay? All right. So how do we prove that this one vanishes? What we're going to do is we're going to divide it by this known polynomial. Okay? So I'm going to take my polynomial here that's supposed to vanish. I'm going to divide it by something that does vanish by definition. And if both of them vanish, they're going to have all the same roots. All the same roots are going to cancel out. And I'm going to end up with a zero polynomial. And if they're not the same, then some of the roots will be different. And when I do the division, either I'm going to get a polynomial, but it won't be the zero polynomial, or I just won't even be able to get a polynomial at all. I'll end up with a rational function or something else. Okay, so what I'm going to do is all right, we'll get started again. Okay, so I made a small mistake, maybe not so small. If you're watching the video, I'm just going to go back and I'll splice this start of this back to like where it is, so you won't even see the rest. Okay, so this equation is exactly the same as what I had, but instead of z, I'm going to call it t. Okay. And so what we're going to do is we're going to start with what should be a vanishing polynomial. We're going to divide it by what we know is a vanishing polynomial. I'm not going to say that this is the zero polynomial. It's just some polynomial. Okay? But what will happen is one of two things. T itself will be a polynomial. So this division will work if all the roots in this are the same as all the roots in this. But I know that the only roots in this are the zeros on the domain. Those are the only roots, okay? So the only way that this division is going to work is if this also has zeros on the domain as well, okay? So I'll get t of x is a polynomial. And basically that tells me, if I get that, that tells me that p of v vanishes. The other thing I could get is that it's not a polynomial. So if p of v doesn't vanish, then I'm going to get a rational function. So it's going to be an uneven division. And then that will happen when p does not vanish. Okay, so it has some of the roots are wrong, or some of the roots that are here are not roots here. So maybe the roots at a different value slightly, even just off by one, or that's basically it. So this doesn't have the matching roots, then t isn't going to be a rational function. Okay. Now, if it's not a polynomial, how am I going to prove, basically, how am I going to prove, ultimately I'm going to prove to the verifier that t is a polynomial. Okay. And so what I'm going to do is I'm going to commit to it. And I can only commit to it if it's a polynomial. If it's not a polynomial, I can't commit to it. We've seen this idea before when we do the KZG opening proofs. We do a division, and it either is a polynomial or it's not. And then we either can commit to it or we can't commit to it. Okay. All right. So if I make a commitment to t, so that's commitment, this proves it's a polynomial. Okay, so at some point in the near future, I'm going to do that and that's going to prove that it's a polynomial. Okay. Now, what I can do with this equation is I can rearrange it. So all I'm doing is I'm taking the denominator and putting it on the other side. Then let me just write it this way first. Then I'm going to move everything over to the left-hand side. And this will equal 0. Okay. So all I did here is I manipulated the polynomials, or just sort of moved things around so I get a 0 here. Okay. Now, what does it mean that it equals 0 here? What that means is that, like, it doesn't matter what value I put in here, as long as it's like mod q and all that stuff. So if I put a 1 in, it will equal 0. If I put a 2 in, it will equal 0. If I put a 3 in, it equals 0. If I put a 4 in, it equals 0. So this is what we can think of as the 0 polynomial. Okay. So it means that this is 0 at every value. Okay. All right, so far, I'm going to write this all out succinctly, but just so that we're following along. We did some manipulations here. We got this v polynomial that's supposed to be 0 everywhere. Then we took the v value, the polynomial that's supposed to be 0 everywhere, we divide it by something that we know is 0 everywhere, and we get this t polynomial, okay? And then what I'm saying is that this polynomial that I know is 0 everywhere, multiplied by this t polynomial that I computed, minus this v polynomial that I'm asserting is 0 on the domain, is going to equal 0 everywhere. That equation will equal 0 everywhere. Okay? And if I can prove to you that this equals 0 everywhere, then you can kind of unwind that logic and say, well, if this is 0 everywhere, then it must be the case that t is a polynomial. And if t is a polynomial, it must be the case that this divides this. And if this divides this, then it must be a case that this is 0 on all values of the domain. And if this is 0 on all the values of the domain, that means that this equation equals 0. And if this equation equals 0, then that means the addition gates in my Plonk circuit were done correctly. Okay, so we'll write out that sort of rationale. Okay, so what we did is we took a problem of like these add gates are correct, and we turned it into here's this equation and it's 0 everywhere. Okay, but I still need to prove that to the verifier. Okay, outside of what the verifier will do exactly, just in terms of intuition, if I come to you with a polynomial, I say this is 0 everywhere. Okay, how could you check whether it's 0 everywhere? Okay. So let me give a bad idea before the good idea. The bad idea is I could open it at every point of the polynomial and show that they're all 0. Okay, but that's going to be very expensive because the number of points on the polynomial are different. What I could do instead is I could just choose one random point, open it at that random point. If it's 0 at that random point, does that mean the whole thing is 0? Probably great overwhelming probability. Why? Well, I know the degree of the polynomial roughly, right? I know how big the circuit is, and that sort of defines the degree of the polynomial. And remember, a polynomial can only be 0 at a certain number of points, which is the degree of the polynomial. Okay? So even if the degree is 1,000,000, there's only 1,000,000 points where that polynomial can be 0, right? But the number of points on the polynomial when I use a real q from an elliptic curve is, more than the grains of sand on Earth, right? And so the chances that this equation ends up, by the way, this is a polynomial. Like this is a polynomial, this is a polynomial, this is a polynomial. All I'm doing is multiplying and subtracting. That always gives me a polynomial. Yeah. And so, so this is a polynomial, and the chances that that polynomial just happens to be 0 is very, very small. It's going to be the probability of 1,000,000, which is the degree of my polynomial, divided by 2 to the 256, which is the number of q values that I have, and it's just so small. Okay, so that's what the verifier is basically going to do, is they're going to pick a random point, and they're going to try and check all of these equations. They want to check that this equation is true, and they want to check that this equation is true. Okay, but this is the key. They don't have the polynomial, so they can't check them. Okay, but what they do have is the commitments to the polynomials. So the question is that enough? Can they check that these equations are correct if they only have the commitment to the polynomial and not the polynomials themselves? Okay, and so we're going to show that that's the case itself. Okay, so I'm finally ready to write out like sort of the protocol. Okay, so this is the proof. Technically, we call it an argument. I'll write that. The A in SNARK is argument. For technical reasons that you don't have to care about. Argument that add gates are correct. Okay, so we have P is the prover, and verifier V. I'm going to describe this as an interactive protocol. So that means the verifier is going to do something. They're not just going to receive the proof, but then later we'll talk about how to get rid of that assumption. Okay. So the prover is going to send to the verifier a commitment to this key array, PC PC is an array. I'm just going to call that KC. And I'll just note that KC is the commitment to the polynomial I need another bracket. Okay. The verifier will send a commitment to the selector polynomial for where all the addition gates are. Okay. So that's this, or sorry, it's this polynomial here. Okay. So the verifier now has this polynomial locked in, and they have this polynomial locked in. I'm not going to send commitments to these two because I'm just using it's this with sort of a multiplication involved. If I give you this, this is just a rotated version of it, so you kind of already have it already. So I have to do something with the rotation later, but I'm not going to commit to it. If I sent you these two commitments, then I would have to prove to you that they're right, that it is a rotation of the other. So I'm going to take care of the rotation in the protocol itself. Okay? So I'm just going to send you these two commitments for now. Okay? Then what I'll do is I will, okay, so what the prover is going to do is they're going to compute this T polynomial. I'll write it in. I'm not writing everything the prover is doing, like how they get C and S, but anyways. They're going to compute T. T is PV over this to the k minus 1. And remember that PV itself is this equation here. so they compute what this t value is. Then what the prover is going to do is they're going to send to the verifier a commitment to that value as well. Okay, good so far? All right, now this is where the verifier is going to come in. What the verifier is going to do is they're going to send to the prover a random point. I'll write it as zeta. So this is a random point. By point, what I mean is a x coordinate. So it would be from ZQ. Okay, not necessarily on the domain. In fact, they'll actually go out of their way. If they choose one at random, it's not going to be on the domain anyways with overwhelming probability. But if they so happen to pick one on the domain, they'll change it. They'll do it again. Okay, so it's a random point. It's an x coordinate, and it's not in the domain. The reason why we don't want it in the domain is I'm going to start opening some of these commitments at this point. And if it's on the domain, what that means is I'm opening some of these values. And those are intermediate values. They're private, right? If I open things that are off domain, then it has nothing to do with the circuit itself. Okay. Then what the prover is going to send to the verifier is the opening of some of these commitments at certain values. Okay, so it's going to take KC and it's going to open it at this value. Okay, so what that means is that the polynomial of C at lambda equals whatever the value is here. I'll just write Y. Yeah. Okay, I'm not going to write anything. So it's just going to open this value here. Okay, I could introduce a bunch of notation, but it's kind of pointless, or it will just make it more complicated later. Okay, so I open it at this value lambda, so the verifier now knows that this is true. How do I do this opening? So I'm going to use KZG. So KZG has this ability to open a commitment at any point. When I open this commitment, there's also a little protocol there, right? I send you a quotient value, you do this pairing between the two values, and you check something, and then you're like, this value is correct. I'm skipping that here, okay? So I'm just writing it as a single line, but know that it's not back and forth, it's just you send it in one direction, but the prover's sending a bunch of stuff to prove that this opening is correct, okay? Then what the prover will do is they're going to open the same polynomial, but this time they're going to open it at this times omega. Okay, so the verifier will learn this times omega. Then they're going to open it at omega squared times lambda, or sorry, times zeta. Then they're going to open t at the same value at just zeta. So the verifier will learn what t of zeta is. And they're going to open the selector polynomial for the addition gates, also at the same value. Okay. Now, what's the verifier going to do? So they have an opening at all of these points. Look at this equation. Basically, they know t at zeta. They don't need an opening. They already know. They can put the value zeta there. Okay? They can put zeta here. They have s plus at zeta. And then they have pc at zeta. They have pc at zeta times omega. And they have pc at zeta times omega squared. Okay? So what they can do is they can check this equation. So what they can do effectively is, I'm going to say check. They can put a zeta in all of these boxes. And then they can check whether this relationship holds for that value zeta. So that doesn't look very clear, so I'm just going to draw it out. I'm going to also move everything over to one side. So what they're going to check is that s plus at zeta times pc at zeta plus pc at zeta omega plus pc at zeta times omega squared minus t at zeta times zeta to the k minus 1. Okay, and remember k is 15 in this case, or however big your thing is. Okay, now these are all numbers, so zeta is a number, it's like 17. Omega is a number, it's 22. All of these openings. So I actually don't know this polynomial, I just know that when you open this polynomial at the value 17, you get 32 or whatever. So these are all just numbers, and I just fill them in, and then I just ask myself, is this equal to 0?
One of them is the minus, right? The last piece of card.
Yeah, so this is,
Or
oh yeah, I see what you're saying. Yes, thank you. All right, so I'm just going to draw this in a box. This is sort of the intuition for sort of the optional thing. But what the verifier is going to do is they're going to check whether this equation equals 0. Okay? If this equation equals 0, then we have to sort of uncurl it. But what that meant is that this relationship holds. And again, if this relationship holds, it means that this divides this. And if this divides this, it means that this thing vanishes. And if this thing vanishes, then that means that the AND gates are correct. Yeah.
So does the verifier know the order?
Yes, yeah, exactly. Yeah, so they do. Yeah. So K is something. Yeah. Let me add it here. It would be a good addition to add here too. I'll call this K. Yeah, so they know omega and they know K. Also, by the way, if you know omega, you can also just compute K. But it saves time if someone tells you what it is. But yeah. Okay, so this was a lot of work to get to this point, but this is the protocol. Now let's think about whether this is succinct or not. So the verifier saw a commitment. Okay, so that's just one group element. They saw a second commitment, that's another group element. They saw a third commitment, which is another group element. They were given 5 openings. Okay, so each of these openings comes with another commitment that you have to check, so you get 5 of them. And then they just do some math. Okay? So basically they get 5 openings, 3 commitments. They check some math. And the important thing is we did this for a very small array. Okay? So we did an array with 15 elements. Let's say this was 15 million elements instead. Does the size of this change in any way? So the commitment is the same, right? The commitments are always the same size. I pick a random point. The opening proofs are always the same size. And so what I'm checking is always the same size, okay? So it doesn't, this protocol is it's the same size. It takes me the same amount of time to check everything, whether it's 15 or 15 million, the size of the array. Okay.
The last step is done by the verifier. The last step is done by the verifier.
Correct, yeah. So the verifier, they receive all of these openings, which are just single values. Yeah? And then they just check whether, for just these single values, whether this equation holds or not. And then with high probability, if it holds with this equation, if this equation holds at this random point, it's going to hold at all points on the polynomial. That's the inference. Okay, now it does change for the prover. Okay, so the prover, they had to interpolate these polynomials and get the coefficients and things like that in order to make the commitments. So if we go from 15 to 15 million, at this step, when the prover has to interpolate this thing, now it's more expensive for the prover, a lot more expensive, right? N log n, more expensive. So it's not free, like SNARKs, they're not free for everyone, okay? What you're doing is you're shifting, you're making the prover do a lot more work, so the verifier has to do a lot less work, okay? So anyway, so that's something to keep in mind, especially when you think of the use cases of zero knowledge. So sometimes you don't have a choice but to do zero knowledge because some of the inputs are secret. But for the kinds of things where you have the choice of using zero knowledge or not because everything is public, a good scenario would be like, let's say there's lots of people that are checking the exact same thing. If they're all checking the same thing, then one prover can spend a lot of time doing a proof once, but then the 10,000 people that are checking now, they can save a lot of time because they're just checking a proof rather than checking that the whole thing was done correctly. So when you have repetition of checking, that's one area where zero knowledge works really well. It's not the only area, but that's an example of one area. Okay, questions about this?
Could you write down, maybe in a short form or whatever, the chain of reasoning that ends, if the
Yeah.
equation vanishes, then the AND gates are correct?
Yes, thank you. Okay. So let me say, what does this prove? Okay, so the first thing that we know is, all we know is that this equals 0. Okay, so that's the first. The verifier knows for sure. They don't know necessarily what this means, right? But they do know that they did a bunch of math, and when they check this equation, it equals 0. Okay, so from here, what we can do is we can infer that if this equation holds at lambda, it will hold at all all points on the polynomial. So I'm going to go back to boxes here. Boxes mean that you can put any value in here and it will continue to hold. Okay, and how do we get from 1 to 2? That's the Schwartz-Zippo lemma. Okay, I won't go over it again, but it basically says that things that hold in one part of a polynomial probably hold everywhere, because there's only so many roots, and it also depends on this being a random value as well. So if the verifier knows that it's random, then it's okay. Okay, so this equation holding on all polynomials, what that means is that t is the correct division of these two things. Okay, so I know that t
Are we going like backwards?
sorry, the
Are we going like backwards?
yeah, backwards reasoning to the statement. Yeah, that's it. Okay, so this is just rearranging the equation. So I didn't do anything logically from here to here. But the thing I know about t is I know t is a polynomial. Otherwise, I wouldn't be able to serve up a commitment to it and open it at a random point. Okay, so if t is a polynomial, then I know that this division is even. I'll just write it here. It means that this is an even division. And I'll write by this equation here. All right, if I can evenly divide by this, what that means is that the roots of this and the roots of this are, I don't want to say the same, every root here is also a root here, okay? So whatever roots this also has the same roots. It might have extra roots on top of it, I don't know, but it has all the same roots, okay? So that means that this equation has roots everywhere that this equation has roots. Okay, then if this vanishes on the domain, which it does, then this must vanish on the domain as well, because vanishing just means it has zeros at certain points, which means that it has roots at the same points. Okay, so then therefore that implies that this vanishes on the domain. And that implies that next thing I'll do, I'll get rid of the selector value. So I'll just say that this equation here equals 0 when the selector value equals 0, the same value. And we don't know what happens, because at all the other values, the whole thing ends up being 0 because when you multiply by S0. Okay. So what this means is that if the selector value, sorry, I should say is 1. Yeah. If the selector value is set to 1, then this equation holds. Okay. And so what that means is so I'm going to start throwing in some English. So if this index is the start of an add gate, then this equals 0. That's what it means for the selector to be 1. And then what I'm going to do is I'm going to turn this equation into math. So I'll say that the left input plus the right input minus the output equals 0 for that gate. Okay. And then finally, that's basically the definition of what it means for the add gate to be correct. So I'll say the add gate is correct. I'll say correctly traced. That's sort of what we talk. Trace means that I put the 3 values in correctly. Do it. Okay, there's one side topic that I want to talk about now. And then once we see it here, you can imagine everywhere else that it shows up, you can do it the same thing. So let's go back to this. So we have the prover and the verifier. I send some commitments. The verifier picks a random point. The prover opens a bunch of stuff. And then the verifier checks an equation. Okay? Let's say there's a scenario where the verifier is not around. So I want to prove, let's say I want to prove something like I received an email and it has this content and this email is signed by this person. So I want to issue that proof and I just want to put it on my website for anyone to visit. Okay? So what I can do is I can start the proof, I can write down these values, but then I get stuck here because the verifier has to give me a random zeta. Okay? Once I get the random zeta, then I can open these up and I can post the proof. Okay? So we call this an interactive protocol because we need something from the verifier. Okay? Now, if I know ahead of time what this zeta value is, okay, as a prover, what I could do is I could try to arrange these polynomials so that this equation holds at zeta, even though it doesn't hold at any other value. Okay? So it's really important that this is a random point itself. Okay? So I'll just note here. We'll call this non-interactive. So far, prover needs zeta from verifier. Okay. If prover knows zeta before committing, okay, they can basically trace the circuit wrong and still have the proof go through. I'll say, but still have equations hold at zeta. Okay. So like they could put additions in that aren't additions or multiplications in that aren't multiplications. Basically, they could do anything they want. So they could prove that the output is different. That's probably the easiest thing to do. So maybe I want to prove to you that the output of this is 34, even though it's 32. So then I'll hide the mistake in some of these values being wrong, but then when I put the proof through, it won't work. Well, the verifier knows that, so this is a good question. The verifier knows that there's a 32 sitting in this, at the end of this array. Does that mean that 32 is the output of this circuit? It just means that the prover put a 32 where the output should be, but it doesn't necessarily mean that that 32 was computed correctly. Yeah? So it's a good question to think about. So like the fact that there's a 32 sitting here just means that the prover put the 32 in the right spot, but it doesn't actually prove that this 32 is the correct multiplications and additions of all the inputs. Yeah?
Basically, we don't want them to know the data before that, right?
Yeah, so before they commit, we want them to commit to this, and then we're going to test whether they did it right with a random zeta. Okay, so let's look at these two properties. So the prover needs zeta from the verifier. If the prover knows it ahead of time, then it's just the whole thing doesn't work. Okay? From this, I want to conclude that therefore the prover could not pick zeta themselves. If the prover picked zeta themselves, it would make it non-interactive. Now you don't need the verifier, but it seems that it would break the second property because now they would have a chance of knowing what zeta is ahead of time, right? And then then the whole proof is off. The soundness of the proof doesn't work.
So it has to be interactive.
So it seems like it has to be interactive, okay? Do you have any idea of how we could get around this?
So the prover makes the commitments and then chooses the zeta randomly, but how does it prove they took it randomly?
That's another thing too, yeah. So that's another argument for why the prover, so even if the prover said, here's the zeta value I'm using, I promise I took it randomly, right? How do you know that? Okay, so there's two solutions here. One of them depends a lot on timing and the other one doesn't. So the first one we don't like, but it will warm you up to the idea that maybe something non-interactive is possible. So the first solution we can use is something called a beacon. Basically, think about the prover posts all their commitments, and somehow that's time stamped. So everyone knows that they chose those yesterday. Okay? Then what you do is you go over to, I don't know, the stock market, and you take all the prices of the S&P 500, the closing prices today, you hash them together, you get a number, and you say that's the number of zeta. And there's no way that you would have predicted that unless if you're a financial genius and can predict stock prices. Okay? So we use a public source of randomness, but the timing matters a lot. You have to know that I committed to those things before I saw that stock price. Okay? If I see the stock price and then change the commitments and go back, then I can make the whole thing work, kind of thing. Okay? So generally, I don't know when someone posted something. If someone posted something on the internet, I don't really know, unless if I trust someone to timestamp it, or I trust Wayback Machine, or whatever. It's hard to determine, just without looking at anything and not trusting anyone, when a particular message was posted. Okay? Could be newer than it seems. So that seems like it's not going to work, but it would be kind of a valid approach if you saw the commitments first and then you saw it after. Okay? All right. Now, anything that I just said, does that give anyone an idea of a different way that we might solve it? I'm not expecting you to know this because it's a very famous cryptographic result, but there is a way that maybe you might have seen before or something. Okay, so this is called Fiat Shamir. That's the name of it. It uses something called hash functions that we've talked a lot about, but we've never really, I don't think we ever sat down and said, this is what a hash function is, and this is its properties. I'm going to say them very quickly. So the hash of a message equals y. You'll learn this in 6110, 6120. So at some point, unless if you're in quality, you're going to see this. So I'm not going to spend a lot of time on it. Message can be any size. Output is fixed. And it has two properties. The one property that we care about is if you see the output, you can't compute the input. So it's a one-way function. There's another property that says you can't find two m's that produce the same y. That's collision resistance. We don't really care about it. Okay. So there's this cryptographic function. It has these properties. Okay. And so what the Fiat Shamir says is what the prover does is the prover computes, or yeah, I'll put it as computes the commitments. So we had a k to the c, what did we have? st. Okay, so they make all the commitments, okay? So that's step one. Two, what the prover does is they do choose zeta themselves. Okay, but they're not free to choose any random number. What they're going to do is they're going to choose a hash of basically all the values they've computed so far. So all of these commitment values. Plus you normally throw in, like you would say what Q is and what omega is and basically everything about the protocol. Okay, so I'm going to write the word full transcript. Basically, everything that's public about the protocol itself, you throw in as well. And you hash it all together, and you get this zeta value. Okay? Then, now you don't need the verifier anymore. So then you can complete the proof. And post it. And so the whole thing is non-interactive. Okay, so why does this work, or why is this secure? So there's two things. The first point was, how do I know that the prover chose zeta right? Like if they just make up a number, how do I know they chose a random number? Well, here, because the verifier will check this. So they'll check that zeta is actually the hash of all of this stuff, okay? So I'll note here the verifier needs to check this. Okay, the second thing, the harder property is like, why does this mean I can't predict what zeta is going to be? Okay, I can sort of predict it. I can compute what zeta is going to be. Okay, the problem is I have to commit first. So I have to commit to a bunch of polynomials that are maybe wrong. Then I hash it. I get a random value. And then the chances of my polynomial being right at this random value that came out is just like so overwhelmingly small, right? Then I can throw the whole thing away and I can go and I can change my commitments so that they work at a different value. But then when I commit the hash, I'm going to probably I'll get a completely different zeta value, okay? So I'd have to sit there and grind out, I'll try a commitment, see if it gives me the right zeta, try another commitment, see if it gets me the right zeta. That is possible. So you can grind out a solution to Fiat Shamir that would break the whole protocol. But if the size of the output of the hash is big, so let's say it's 256 bits, then grinding it out is sort of the same as trying to guess your secret key. It's going to take 2 to the 256 work. It's infeasible. No one can do that. Okay? So that's essentially why it works. Now, the other assumption we're making here implicitly is that this acts like a random function. So we sometimes call this a random oracle or a random oracle assumption, but it basically says that, I'm just going to make this small h because I have a small h up here. It just says that this, the outputs are random. Yeah, so you can't predict them. Yeah.
How will make sure it's within Z key?
So that's a good question. So what you can do is you can mod it by Q at the end. Yeah. So yeah. So this is technically, I'll write in mod Q. Usually, so the reason I didn't even think of asking that question is the output of a hash is a 256-bit number, and Q is also a 256-bit number, and so they're almost the same, just slightly different. Okay, so SNARKs, the N in SNARKs is non-interactive. So it might actually be a good time to like just go back to what SNARK means, because now you can kind of see what it means. Okay, so S means it's succinct, and that's, we've seen that. So if the array is 15 or 15 million, it's the same for the verifier. So succinct for verifier. N means non-interactive, which means you can just spit it out. Arc means argument or proof. So usually, like informally, we talk about proofs, like you prove this, I'm proving to you that this vanishes or whatever. Technically, they're arguments, and there's a technical difference between an argument and a proof, which depends on how strong the prover is. But if you assume prover and verifiers are computationally bounded, there's no difference in practice. Is there an E in argument or not? I can't decide. Okay, anyway, so it's an argument of knowledge, which is kind of a weird thing. What does that mean to argue that you know? Well, the thing is, I'm proving to you that I know a circuit trace. Okay, so I'm not showing you the circuit trace, but I'm proving that I know it, and when I filled it in, all of these properties held about it, right? So I know a way to put a bunch of purple values into this array, and it's going to be that this is true, that the inputs are correct, the outputs are correct, add gates, multi gates, and wiring is correct. Okay. So that too. So that's another good question. So how do we do the multiplication gate? Well, the only thing we changed was the vanishing polynomial, like the statement of the vanishing polynomial. So you can look at this as a general recipe. This is the recipe for this vanishing polynomial. But if you switch out this vanishing polynomial with any other vanishing polynomial, then it's the same recipe. The only thing that changes is that here, when you open points up, you have to make sure that you're opening a point, like all the points that you need for this vanishing polynomial. Yeah, so all the terms that are in this vanishing polynomial, you have to open a point up for. So when we switched to multiplication, the only thing that changed was this changed to a different array, and this sign changed to a multiplication. So it's literally exactly the same protocol. It's just that this, at the very last step, you do a multiplication instead, and you're getting the opening of the multiplication selector instead of the addition selector. Yeah, so the denominator is the same. The division of the two is the same. Moving everything to the equation, showing that it equals 0 is the same. Exactly, yeah. So this addition turns into multiplication. Yeah. So I'm not going to draw the whole thing out for the multiplication as well. So thanks for asking the question. I'm going to consider now at this point that we now know how to do this, and we also know how to do this. Okay, so the thing that we'll spend the next 2 lectures on is trying to prove that the wiring is done correctly. Okay, so that's all I had for today. Is there any other questions? Good. All right, so I'll see you all next week.